morning, everyone. If we could just settle down a little bit, thank you. Morning, everyone. My name is Mark Ferreri. I'm the Supervisor of Humanities, and on behalf of the RHS learning community, we are honored to offer a special presentation today. I'd like to thank the Network for Responsible Public Policy and its president, Ms. Rhoda Sherman. The NFRPP is a nonpartisan and nonprofit organization whose mission is to provide evidence-based, credible information and education programs on key public policy issues for the general public of all ages. In this current era of information overload and the charged political rhetoric, the NFRPP brings speakers who are distinguished experts in their select fields to bear on helping a knowledgeable citizenry help maintain and foster our viable and strong republic. It is in this spirit and with gratitude to the Network for Responsible Public Policy that I am honored to introduce Dr. Kevin Trenberth, a distinguished senior scientist in the climate analysis section at the National Center for Atmospheric Research. A native New Zealander, Dr. Trenberth received his doctorate from MIT and has played a prominent role in most of the Intergovernmental Panel on Climate Change Scientific Assessments and has extensively served the World Climate Research Program, most recently as the chair of the WCRP Global Energy and Water Exchanges Project. He has published over 544 articles or books and is one of the most cited scientists in the field. Today, Dr. Trenberth will explore the role of El Nino, climate change, and other influences on weather and climate. He will explain how these are linked phenomenon and what they imply for the future. So please provide a warm RHS welcome to Dr. Trenberth.
Good morning, everyone. Sorry I'm a little late. I got hung up in traffic getting here. I should say g'day, right? I'm from New Zealand. But also I'm from Colorado. How many of you have been to Colorado? Good, because there's some pictures here I'll show. Do you think the weather's been weird? All right, this is where you get to participate a little bit. I want to see if you can respond to this. Knock, knock. Who's there? Anna. Hello. Another snowstorm. Knock, knock. Stella. Stella, another snowstorm. So Stella was the name of the storm given to this storm that occurred a couple of weeks ago where you had a snow day, right? All right. So, did you enjoy that snow day? Yeah, all right. Do you know what El Nino is? You'll find out a little bit about it. I can't go into too much detail. And we're going to talk a bit about global warming and its influences on the weather and what these things mean for the future. So, one of the summaries we might have is if the planet Earth went to see the doctor. So the planet is running a fever. It has high temperatures. In addition, we can observe that the composition of the atmosphere is changing. The carbon dioxide is increasing. Whoops, went too fast there. The diagnosis is that these two things are actually related to one another, and that the human activities are causal because they're responsible for the increases in carbon dioxide in the atmosphere. And so then the prognosis, the outlook, is for more warming at rates which can be disruptive and will cause strife in the climate system. This is the climate system you guys are inheriting from my generation. You ought to be pissed off at our generation. Anyway, we'll come back to that. The treatment is sometimes called mitigation, which is reducing emissions of carbon dioxide into the atmosphere. That's the burning of fossil fuels in particular. And adaptation is the other aspect of it, which means really planning for the consequences in various ways. So this is one of the things that I want to talk to you a little bit about today. But before I do that, let me just say a little bit about the role of people like myself as scientists. 97% of scientists agree that climate change is real and it's caused by humans. But the data that we deal with, the observations, are certainly of mixed quality and length in different places around the world. But there's all kinds of information, which I'm going to run quickly by you, that supports the story I'm telling you that the planet is warming and it has various symptoms in a whole lot of different variables, a whole lot of different fields, temperature, precipitation, sea level, and so on. And it leaves no doubt that there's a human influence on climate. What I'm not going to talk to you about, but which you might like to address in some of the Q&A afterwards if we've got time, is what we might do about this. And this is where the politics comes in. This is where some of the nasty stuff that you may have heard in the media comes in. So the planet is warming. What is causing this warming? Here's some examples here. We generate electricity. There's all kinds of industry. There's airplanes. You're no doubt responsible for some of this. And the fact of the matter is that the answer to this question is we are. So it's the emissions of carbon dioxide into the atmosphere. So here's the carbon dioxide record. This was actually started by a colleague, a friend of mine called Dave Keeling at Mauna Loa, the top of the highest peak in Hawaii, the island of Hawaii, where it's well away from all sources of industry, and started measuring carbon dioxide in 1958. And so this is the record that we've got up till about a year ago. And you can see a sawtooth character to it. So that's the up and down of the breathing in and out of the planet, so to speak. So in the springtime now, outside, the plants are beginning to perk up and green up. Photosynthesis is happening. It takes up carbon dioxide out of the atmosphere. It draws down the carbon dioxide in the atmosphere, and it uses the carbon in that carbon dioxide to generate leaves and twigs and trunks of trees and so on. And at the same time, it puts some oxygen back into the atmosphere. So that's the drawdown in this sawtooth character that we see here. But then in the fall and in the winter, the leaves that are on the forest floor and so on, and all of the debris in the gardens decays. And that puts more carbon dioxide into the atmosphere. And so it goes back up and down. And so that's the annual cycles. That's the sawtooth character there. And that's huge, actually. That's a huge amount of uptake and release of carbon dioxide every year. But superimposed upon that, you can see that there's a very strong trend. And so at the beginning of the record, the trend was sort of like that. And then you can see some other examples of the trend. The fact is that the rate of increase of carbon dioxide is increasing. And that is in spite of efforts to turn this down in the other direction, to cut down on emissions of carbon dioxide. That one of the mechanisms for trying to do that was called the Kyoto Protocol. And I won't go into detail about that, but there have been substantial efforts to try and bend this back down in the other direction. And instead, the highest increases have occurred in the last 2 years. The last 2 years, there's the biggest increase, 3 parts per million by volume. So these are parts per million by volume. The pre-industrial level is estimated to be 280 parts per million by volume. And so we've gone up by more than a quarter in carbon dioxide in the atmosphere. So these are facts. All right, so here's the global mean temperature record, an estimate of it. It's not so reliable before about 1958. 1958 is when we started making measurements in Antarctica. Before then, we don't really have measurements in Antarctica. And so there are fewer measurements as you go back in time, but we believe this is a reasonable estimate of what's happened on a global basis as you go back in time to, in this case, 1880. This record is put together by NOAA. The 0 on here corresponds to the 20th century, 1900 to 1999. You can see there's lots of wiggles up and down, zigs and zags, but you can see also there's a steady increase overall. So if you prefer degrees Fahrenheit, I put a scale on here in degrees Fahrenheit, so it's not quite in the right spot. 0.55 degrees Celsius is 1 degree Fahrenheit, and this top value in 2016 is 1.7 degrees Fahrenheit above the 20th century. I also put on here the pre-industrial level, which is about here, and so that's 1.1 degrees Celsius. It's 2 degrees Fahrenheit above the pre-industrial level. So that's the extent of the global warming in terms of the surface temperature record. So now I'm adding the annual values of the carbon dioxide on here, and before 1958, we're using bubbles of air from Antarctica and Greenland that trapped the carbon dioxide, and we can analyze that and see how much carbon dioxide there was in it. And that's where we get this number, 280 parts per million by volume. Let's see if I can use this pointer. So here's 280 over here. And that's the pre-industrial level. And again, the 0 corresponds to the value of the 20th century. So this is the overall increase. And you can see we're now over 400 parts per million by volume. So 280 to 400, somewhere around about here is halfway, right? If you go across here, you can see, well, half of the increase has occurred since about 1985. So there's a gradual increase with industrialization through to World War II, and then after World War II, it really took off. And half of the increase has occurred since 1985. That's pretty recent. So I put these together to suggest that there's a relationship between them. Now, obviously, the carbon dioxide changes aren't responsible for the wiggles from one year to the next, but the overall changes are related to the carbon dioxide record. And we can actually prove that in my institution by using climate models. And I'm not going to say very much more about it other than to say that there is a real relationship between these, and it's a causal one. The highest 12 months on record is this period from September 2015 to August 2016. And that actually, I'll go back, there we are there. So there, that's the warmest 12 months on record. And this was in part because of the big El Nino that we've recently had. So if we have this increase in carbon dioxide, which sort of acts as a blanket, it traps extra energy in the system. Where does that energy go? Where does that heat go? Well, some of it warms the land and the atmosphere. Some of it goes into the ocean, and then the ocean expands, and that causes a rise in sea level. Some of it melts land ice. These are glaciers and Greenland, the big ice sheets. Some of it melts sea ice, Arctic sea ice. It doesn't increase sea level because the sea ice is already floating on the water, and then it warms the water. And the biggest complication is that some of it evaporates moisture and changes rainstorms and cloud, and therefore it can change the brightness of our planet. I'll talk a little bit about that, some of the consequences of that, because those are some of the consequences that have the biggest effects on us. But it turns out the memory of all of this, over 90% of it, about 92% of it, of this extra heat goes into the ocean. So I'll show you that very shortly. So if you have extra heat, what happens? What happens if you try to heat up your body? If you sit in front of a big fireplace or something like that, your body starts to sweat. And the evaporation of the sweat, the perspiration, keeps you cool. It's called evaporative cooling. It works very well. And so in the West, in Colorado and in California, we can use evaporative coolers. So these are sometimes called swamp coolers. They put more moisture into the atmosphere, but they keep the house cooler as a result. It doesn't work so well in the east here because there's too much moisture around. But this actually works quite well for the planet because 70% of the surface of the planet is the ocean. And so a lot of this heat goes into the ocean and it evaporates, produces evaporative cooling of the ocean, keeps the ocean cooler, but it puts more moisture into the atmosphere. What happens to that moisture? It has consequences for the weather. And so another example, if it's been raining, as it has been in the last few days, on and off, and then the sun comes out, the first thing that happens is that the puddles dry up. And then the temperature goes up. It's not quite that divided, but to a large degree, that's what happens. And I don't know if you've been hiking somewhere, especially if you go hiking in the mountains out in Colorado, and you don't take a water bottle, you can end up with heat stroke. Having a water bottle, keeping plenty of moisture in your body allows you to sweat, to offset the heat that would otherwise build up. And so water is the air conditioner of the planet. It plays a very important role in that regard, but it means it has consequences for things like rainfall. So some evidence for climate change. These are relatively old slides. The top one shows 1941 and 2004 in Alaska. The one down below is in Austria, 1900 versus 2003. But there's many examples of these. You can find them on the web, where glaciers around the world are retreating substantially, another indication that the planet is warming. And then we can look at Arctic sea ice. Arctic sea ice has, Arctic sea ice has decreased by over 40% in summer. The peak, the minimum in sea ice is at the end of the summer because the summer heat melts it down. And the lowest value so far has occurred in 2012, and you can see the time series here. There's an overall general trend though, and right now the values are the lowest on record for the wintertime or the springtime. And so the prospects are that this coming year we may well go below the 2012 value, but there's some weather aspects that come into play on that. But Arctic sea ice is decreasing. You can see the graphic down the bottom here, what the average was prior to, say, about 1970. And then in 2012, that there was relatively less Arctic sea ice. So what's happening in the Arctic? Well, there is potential ways of getting across from the Pacific into the Atlantic through the Northwest Passage and so-called, but also various countries are expressing interest in mining various elements from the floor of the Arctic Ocean, including more oil, which would make the problem even worse. This is the ocean heat content. This is rather hard to compute, and the values before about 1980 are not as reliable. You can see there's a spread in pink around the black bar here, which indicates the uncertainty, and the uncertainty gets less in recent times. We've got now some 3,800 floats, autonomous floats that go up and down and make measurements in the ocean, recording temperature and salinity, and then when they get to the surface, they telemeter that information back to satellite, and we can compile really good estimates of the ocean heat content. So the ocean heat content has increased substantially over time, and this is what I said before, this is the memory of all of the past climate change. And so the oceans are warmer. That means the sea temperatures are in general warmer. There's a lot of other things going on that affect the sea temperatures on a day-to-day basis. But that means it influences the weather systems. So we'll say a bit more about that in just a minute. So another aspect of that is that sea level is going up. This is an estimate of global sea level rise. But prior to 1992, we had estimates only from island nations and from coastal regions. We didn't have them, sea level over the middle of the ocean. And in 1992, the US and the French launched a satellite called TOPEX that has an altimeter on it that's looking down and measuring the surface of the planet to millimeter accuracy. It's remarkable. We get one value every 16 days. That's what these red dots are, and blue dots and green dots on here are. And then the overall values are given by the black curve when we put them all together. And you can see that sea level is rising, and the rate is, on average, 3.4 millimeters per year. On the right-hand side there, I've got a scale that since we started measuring this, sea level has gone up by over 3 inches. These are solid measurements. So a good chunk of this comes from the expansion of the ocean, and then the rest, about half of it, comes from the melting of land ice that puts more water into the ocean. These two things together are causing the increase in sea level. There's some wiggles in here. It turns out, you know, this is a big El Nino. This is a smaller one. This is a big El Nino. And then this was a big La Nina. I'll say more about that in a minute. So there's some other fluctuations that are caused in here, and it relates really to how much rain there is on land versus how much there is in the ocean. In El Nino, the oceans are warm, and so it rains over the ocean, and there's a lot more drought over Australia and other places. But in La Nina conditions, it rains a lot over Australia and other places, and it takes water out of the ocean, and that's the sort of thing that can result. So 3 inches in what, 10, 20 years, that's 15 inches per century. That's the current rate. Scientists think this could easily double. We could easily get to 2 feet, maybe even more by the end of the century. This puts coastal regions in jeopardy. So one message to you: don't buy a house too close to the coast. Actually, if you buy one further inland, it may become coastal at some point. So one of the other key things, if there's anything that you remember, this is one fact that you might remember. Warmer air can hold more moisture, and the rate is 4% per degree Fahrenheit. Now, this is a percent. It's not an absolute amount. It's a percent. And that means warmer air can hold even more moisture. So this is why when you put your hairdryer on, you put it on warm, right? Because if you blow cold air on your hair, it doesn't take the moisture away anything like as fast as warm air does. And it's not because of the heat of that air, it's because the air can hold more moisture. It sucks the moisture out of your hair. Same thing with a clothes dryer. If you put it on warm or hot, it'll dry the clothes much more rapidly. And it's not because of the heat. It's because the air takes up the moisture and then it gets blown out of the exhaust. And so with global warming, there's more heat. That means there's more drying, as we've said. There's more evaporation, especially over the oceans, which puts more moisture into the atmosphere. But that depends, right? And so the consequences are, at the bottom here, if it's not raining by chance, for whatever reason, we have dry conditions, then things dry out quicker. The drought sets in, it's stronger. There's a greater risk of wildfire as a result. But if it is raining, the moisture tends to be gathered by the weather systems, and it rains even harder. And that's one of the things that happens these days. When it rains harder, or in the wintertime, it can even snow harder. We'll say a bit more about that in a minute. So this is my attempt at fancy graphic. You know, it's just me, so I just have to do these graphics by myself. So here's my attempt to do a little bit of fancy graphics. So we have, say, a parcel of air, and it rises for whatever reason. It might be because it's moving along and it runs into a hill or something, or there's a cold front or a warm front that helps to push the air upwards. And then when it does, it expands because it moves into lower and lower pressure. There's less air above it to put pressure on it, and so it expands. So let's see what happens. Here it goes. And we get clouds and, whoa, lightning. And then it rains like hell. So that's what happens. So I don't know whether you are taught in your classes these days about where precipitation comes from. I don't know if you've ever thought, where does the rain come from that comes out of a cloud? How come sometimes we can get maybe 6 inches of rain, or even more in some places? Is there 6 inches of water up there somewhere? Where did it come from? Well, it turns out, the rain doesn't come from evaporation locally. Instead, it's raining over a small fraction, about 1/16 of the planet at any time. It doesn't rain everywhere all at once. And so what happens is that a storm, and in this case I've indicated a big thunderstorm, it reaches out and it grabs the moisture. And the region over which it's raining, it reaches out about 4 times the radius of that rain region, or about 4 times 4, 16 times the area, in order to grab all of the available moisture and bring it into the storm. And if you're out playing baseball or something on the field in the summertime, and there's some gusty winds come by, say, what's going on? And then you look in the distance and you can see, oh, there's a thunderstorm way over there, but it's 5 miles away, good heavens. Well, that thunderstorm is actually reaching out, grabbing the moisture, bringing it in, and that's what enables it, bringing the air in and its moisture, and that's what enables it to rain as hard as it does. And so if there's more moisture in the environment, which is what happens because the air is warmer and it holds more moisture, then it means that it rains harder. So this has some consequences. So before we go on to show you some statistics on that, let me talk a little bit about mountains. So here we are in Colorado. I've used this as a backdrop to indicate what happens with snow and in the mountains. So even with global warming, there is still winter. The sun still disappears from the Arctic. And so there's a polar night. There's no sunshine in the Arctic. It gets cold. There's going to be cold air. There'll be cold air over continents. The continents radiate to space. So we'll still have summer and winter. What happens when snow falls? Snow can fall up to temperatures of about 35, maybe even 37 degrees Fahrenheit, because the air above the surface is a bit colder. But the biggest amounts of snow occur when the temperatures are about 28 to 32, just a bit below freezing. And in fact, if it's too cold, if the temperature is below 20 degrees, the snow instead takes on a different character. It tends to be very light and fluffy, and it won't bond together. You can't make snowmen or snowwomen. And in fact, what happens is the air gets freeze-dried. And that's this 4% per degree Fahrenheit. If you cool it off from 30 degrees to 20 degrees, you lose 40% of the moisture in the atmosphere. And of course, that's how the weather systems work. That's how they actually make rain. That's how they make snow in the first place. So more snow is actually the result of a warming climate. It means that it has to be just right, though. This is what we might call the Goldilocks effect. Goldilocks and the 3 bears had to have her porridge just right. If it's too cold, the air gets freeze-dried. If it's too warm, it turns to rain. And if it's just right, you can get a big snowstorm. Now, if it's warm, the glaciers retreat. That means the snow cover is less in the mountains, and the snow is bright. It reflects the sun. And therefore, if there's less snow and ice, less of the sun gets reflected and things warm up as a consequence. And so there's a feedback effect. It gets amplified. But we can have more snow in the middle of winter because the temperatures are a little higher. They're still below freezing. But the snow melt occurs a bit sooner in the spring, and the runoff is earlier, and that leaves less snowpack for the late spring and into the summer. that has consequences. It increases the wildfire risk in the summertime, and that's what we're observing, especially in the western half of the United States. So there's prospects then for less water in the summer in many parts of the US and around the world. And that means greater risk of drought, heat waves, and wildfires, and that's what we're seeing. There's also expansion of pests like the bark beetle, and if you've been out in the West recently or if you've flown over it, there's huge expanses of trees that have been killed by this pest, the bark beetle. And the bark beetle used to get killed off by cold weather and doesn't get killed off as much nowadays. And the trees are also weakened because of the dry conditions. So Senator James Inhofe doesn't understand this, and he went into the US Senate a couple of years ago with a snowball pretending, or saying that, oh, look at all this snow. Where's global warming? Well, he was quite wrong, because it turns out more snow is actually a symptom of global warming as long as it doesn't turn to rain. This was a snowstorm, you may remember, from about a year ago, just over a year ago. It was called Jonas, and it affected Washington, D.C. So the panda, the young panda in Washington, D.C., was featured in news clips and so on, was rollicking in the snow, never seen snow before. The two pictures on the left were taken in Hoboken, New Jersey, by my daughter. And the top left is my granddaughter. She turned 5 on Friday, which is one reason I'm out here. So, lots of snow. Thank you. She is cute, I'll give you that. So here's the record for the Northern Hemisphere snow cover. You can see that in October, November, December, and January, the amount of snow cover around the Northern Hemisphere has actually increased a little bit since we had 1966. It's hard to go back before then because we don't have satellites before about 1966. But you see in the summertime, March, April, May, June, July, and August, that there is a considerable reduction in the amount of snow around the Northern Hemisphere. So this is one of the symptoms of global climate change. So this is what I said to you at the beginning. You know, we've looked at snow, we've looked at precipitation, we've looked at ice, and we've looked at temperature and so on. And all of these are changing in the ways that are consistent with our understanding of how they should interact with one another. So here's the actual record for the US now, rather than global. The temperature is at the top here. The purple values are the annual values. And then there's a couple of other lines on there. And down below is the precipitation. Both of them are increasing somewhat. The temperature curve has increased, what, 1.5 degrees overall for the degrees Fahrenheit. And the precipitation has a lot more ups and downs, a zigzag character to it than the temperature one. So let me point out a few things here. Firstly, this is the period back in the 1930s called the Dust Bowl. And it was a famous time. There are some books written about this kind of thing. It was very hot and it was very dry. And so you can see in here some record dry years occurring. Well, there's a couple of others in here as well, but during the summertime, these were record dry years, and they each correspond to record high temperatures. And so, you know, hot goes with dry and even drought. And that's what happened in those times. And that set the records for a number of years until more recently, where we've broken those records. So if I were to characterize the precipitation, I wouldn't say that it's a trend. Rather, I would say it's more like a jump, somewhere around about the 1970s. The exact date that you put that jump varies depending on which season you look at. But somewhere around about then, it sort of jumped to higher levels. I don't know whether you can see the numbers on here, but it turns out that's about a 7% increase in precipitation. It turns out if we went back to the amount of precipitation before 1970, a lot of places in the east would be really suffering from water shortages. We've seen that from time to time. But at the moment, because of the extra precipitation, we're managing to get by. But the east does not look after its water anything like as much as we do in the west and out in California. Water is a valuable commodity. So if you look at 2012, that turns out to be the warmest year on record for the US. Slightly warmer than 2016. You can see 2016 peaking out there, slightly less than that, but 2012 was also extremely dry. The drought that year cost $75 billion, B with a B, dollars. That's the estimate as to how much that drought cost us. And this is the pattern of what it looked like for that year. It was warm, especially in the central part of the country, but you can see even in this very warm year, there were still some places, like in the Pacific Northwest, Washington and Oregon, where it was below normal. And this is the nature of the weather patterns. A different way of looking at this is to say, well, let's see what happens if we take the last 35 years, from 1981 to 2015, and compare it with the first 60 years of the 20th century. This is what it looks like. Here's Hawaii here, Alaska. There's a little patch down here where it hasn't warmed up so much, but it's warmed up in the northeast and all throughout the west and the northern states in particular. And then down the bottom, I've got the overall change in the 5-year extreme precipitation events, and you can see the biggest is actually in the northeast, maybe embracing this area. We're right on the edge here, but big increases in the heavy rains that occur. And not quite so much in the west, and that's partly because of the widespread drought that's occurred in California. So these are the changes that we've actually experienced in the United States. And the prospects are that these things will become amplified, and we'll see more of the same kind of thing as we go into the future. So I thought I'd talk very briefly about the 2015-16 El Nino event. There's a picture there from NASA as to what the sea surface temperatures, departures from normal, we call them anomalies, looks like around about the middle of the event. It was very warm in the central and eastern Pacific along the equator. So the term El Nino is Spanish. It refers to the Christ child, the boy, the little one. And it grew up 150 years ago off the coast of Peru and Ecuador when an annual current that was once called the El Nino current, because it came around Christmas time, came down the coast. It was a warm current. But every 3 or 5 years or something like that, this current became extremely warm, and the term then took on the anomalous event, and that started to be called El Nino. Now, it wasn't until the 1970s that we decided we had to have the opposite of this, and it ended up being called La Nina, the girl. So the La Nina is the cold case in the tropical Pacific. So El Nino refers to a warming of sea temperatures in the central and eastern Pacific. It's really the ocean part. There's an atmospheric component to this. I'll show you the consequences of that in just a minute. And La Nina is the cold ocean phase, and it corresponds to cool sea surface temperatures, below normal temperatures in the tropical Pacific. And these events occur about every 3 to 7 years on average. Now they arise, I don't have time to go into this, but you can ask questions about it if you like, from atmosphere-ocean interactions. The change in the atmosphere changes the ocean, which in turn changes the atmosphere, and it goes on until we have an El Nino event. It causes changes in nutrients in the ocean, so it changes the fish and the fish distribution, it changes seabirds, it changes people, it changes the food distribution all throughout the Pacific Rim countries. And one of the things that happens is it changes rainfall patterns in the tropical Pacific. And when it does that, it's a little bit like a rock in a stream. This is actually a satellite picture of Guadalupe Island where the wind is blowing from the southwest, and you can see waves going way downstream from this. And this is the sort of thing that happens in the atmosphere. So when there are changes in the tropical Pacific, it turns out it affects the waves, the atmospheric waves and the jet stream across North America. It affects the storm tracks. It affects the patterns of weather around the world, in fact. And these are the main patterns that occur. So this is during El Nino. This is December, January, February. This is wintertime. You can see that it tends to be very dry and warm over here. It tends to be very wet in here. It's wet and cool in the southern parts of the US in general, but very warm up in here. And this is what it looks like in June, July, August. So the biggest changes tend to be in Pacific Rim countries, but there are certainly influences that you can track across into Europe in individual events. So if we look at how these things have happened in the past, this is the sequence since 1950. This is actually looking at the sea temperatures in that tropical Pacific region. And you can see they're graded here by degrees Celsius. This is relative to an average value. And there's La Niñas down here and El Niños here. There are 3 very strong El Nino events. 2015-16 is one of them. And we can take this back to maybe 1800 or 1770. And these are the 3 strongest on record. There are no very strong La Nina events. There are some, the La Nina events tend to last longer. Whoops, so here we go. So El Niños are red, La Niñas are blue. They follow in sequence every year or 2. Okay, that's my attempt at poetry. So in the tropics, the weather sort of looks like this. You have either an El Nino event or a La Nina event, actually about 60% of the time. It's very seldom normal. It's very seldom average. You can see it's always going from one to the other. But we don't have seasons in the tropics. This is what we tend to have instead. And so it goes from rain to drought. And this is what it actually looked like in late 2015. This is when the sea temperatures were at their peak. These are in degrees Celsius. And you can see some values in here. This value here is actually 4 degrees Celsius. 3.5 degrees Celsius is 6.3 degrees Fahrenheit. This is very, very warm water. And it has major consequences all throughout this region for all of the fisheries and organisms and so on. This is what it looks like about a week ago. This is actually for March of 2017. So all that warm water is gone, but there's now some very warm water right off of the coast of Peru here. 3 degrees Celsius above normal. It's actually cool out here. There was a brief La Nina. So we can actually look. These are the 3 different regions. This is the region where this green box is, right off the coast. You can see the El Nino wasn't, this is the El Nino back in here. And the values we were looking at in the big ups and downs is this region here, which corresponds to a region out here. So here you can see it's warmed up in recent times, especially in the last 2 months. And one of the consequences is there's been some terrible flooding down in Peru. So this is what happened. There was big flooding in northern Chile in late February as a consequence of this. And then these are pictures from Peru just a few days ago, 19th of March. And I don't know whether you saw this on television. This was on a lot of news clips. But there's actually a woman in here who got carried away in this mudslide and was scrambling to get out of it, and fortunately did, to try and get out of this mudslide. So there's been some terrible damage that's gone on in that region as a consequence of the El Nino event along the coast there. Maybe you can use this next time. All right. So the things that matter for us on a day-to-day basis is not so much the average values, it's more the extremes. The extremes, they may or may not be rare, but when they occur, they may break records. We have values that are outside the previous experience. and things can break. And so we have the situation of adding a straw to the camel's back, and look at the poor camel. Aww. So I thought, since I'm here, I would talk a little bit about Superstorm Sandy. How many of you remember Superstorm Sandy? How many were evacuated? My family were evacuated from Hoboken at that time. So here's some pictures of what happened. There's a great big storm. It was huge at that time. And this is what it looked like from the satellites. And there was tremendous damage along the Jersey shore, as you may well be aware. And this is a satellite picture of that storm developing, going up the coast here, and then moving inland right over New Jersey, right here, and causing tremendous amounts of damage, flooding the subways, flooding the PATH train to New Jersey. So I thought I would run through a few of the events that we've seen in the last year or two associated with this big El Nino. So in the first place, there's been major wildfires in the West, in Alaska, in Canada, in Washington, in Oregon. There were major wildfires in Southeast Asia, in Borneo, in Indonesia. This is Fort McMurray over here in Canada, a major wildfire in May of 2016, following drought that was related to El Nino. And then there was major drought in South Africa with the El Nino. And then this year, we went back into a weak La Nina, and we saw these record high temperatures in Australia, in New South Wales. It's quite a big state. And the whole state averaged 111 degrees Fahrenheit for the high temperature one day. 111 degrees. The minimum temperature at one location was 94 degrees. The minimum temperature. Imagine trying to sleep in that if you haven't got air conditioning. And there were a whole bunch of wildfires. There were 87 wildfires that broke out in Australia just recently. Meanwhile, there have been floods in various places around the world. South Carolina in October 2015, in Chennai in India, then in Missouri in November, December 2015, in Paraguay around the same time. And then we had Houston in April of this past year, Louisiana, big floods in Louisiana in August, and then California, of course, has now experienced flooding, and there was this wonderful tree that you could drive through, and I don't know whether you heard, but the tree fell down because of all of the snow. There were also record numbers of hurricanes and typhoons in 2015, more than anywhere else, more than at any other time. So there were spectacular pictures, like 3 hurricanes or typhoons. As soon as they cross the date line, they're called typhoons. Otherwise, so there's a couple of these, one of these hit Hawaii. And then there was one just recently, I thought I'd go through in a little more detail, Hurricane Matthew in October. And so this is before, this is before, and then this is after in Haiti. And you can see how everything got washed out and the damage that was done. So the damage is in the slide at the top as a typical example. And then there was tremendous flooding in North Carolina as a result of this and along the East Coast. And so this is the precipitation maps. There were places here where the dark blue is, where it's estimated that the amount of precipitation they had was a 1 in 1,000 year event. Now that assumes no climate change, and of course part of that is because of climate change, but it shows you the magnitude of the rainfalls that occurred in association with that event. And now here's Stella. Here's the snowstorm that we had just recently. And so here's some pictures associated with that, with the snow in New York City, in Hoboken, the big bull on Wall Street, and some of the pictures of that storm. So that's all I'm going to talk about in terms of the weather, and then just a couple of other slides. This is the statistics for the last 20 years. The average damage from weather and climate events is $42 billion per year. That's this number here. So there's tremendous amount of damage, and even small changes can make huge savings as a result. if you can be prepared for this. So El Niños occur naturally, but we're beginning to predict some aspects of these, and with good observations and better models, we'll be able to facilitate better planning for this in places like Peru and in the US. But global change is occurring from human activities, and we really need to act to slow down the rates of change and to plan for the consequences. So we could do things like this, maybe? I imagine you can think of a lot of other things. I'd be happy to talk about that in the Q&A. And this is one of my favorite cartoons. This is very appropriate in the political arena right now. From a science standpoint, climate change is happening. It's caused by humans. There's no doubt whatsoever. But the question is, what do we do about it? Do we just live with the consequences? Do we plan for it? Do we try and stop it in various ways? And so I'll stop there and leave this up. There's a little bit of information here about websites if you're interested. Thank you very much. How long have we got?
We got at least a half hour.
We got.
How long would you like to go?
I can go as long as you like.
I'm just going to gauge the audience, see what they
All right.
Okay, ladies and gentlemen, we have some time for Q&A, so hopefully you have some questions for our expert in the field this morning. What I'd like to do is I just have this one microphone. So what we'll do is, if you have a question in orderly fashion, if you'd like to just come up, and you can form a line here, and you can ask your question, and Dr. Trenberth would be happy to respond to it. So the mic is yours, and this is for staff and students. So teachers, feel free to come up and ask a question.
So I know that there's a lot of people that may understand that the climate is changing, but not necessarily agree that it's due to human impact. What's maybe some way that we can try and convince them of that?
Sorry, say the last bit again.
Is there maybe like some way that to convince them otherwise, or to show that human impact is directly impacting the climate?
I don't think I have the slides here. This is the sort of thing we do at my institution, the National Center for Atmospheric Research. So we build climate models. The atmospheric part of a climate model are the models that are used on a daily basis to predict the weather. And so we can predict the weather now out to 10 days, maybe out to 2 weeks in advance with a little bit less reliability. And that forms a key part of the climate models. Then we have to have an ocean model, we have to have a land surface model, we have to have a sea ice model, and so on. We put all these together. And we can, one of the fun things about being a climate scientist is that we can play God to some extent. We can say, what if there's no increase in carbon dioxide, what would the climate have done? And we can see how much variability there is from one year to the next, from one decade to the next. And so the estimate is that the natural variability can be about as much as about 0.2 degrees Celsius from the interactions between the atmosphere and the ocean, the El Nino events, and things like that. The only way we can replicate what has happened in the past is by putting in the increases in the carbon dioxide and the other changes in the composition of the atmosphere. Methane, nitrous oxide, and also the pollution in the atmosphere plays a role as well. And so this is the sort of thing we do. It's another whole lecture to really deal with that, to establish the relationship between these two things. And also that provides us with a basis for making projections into the future. We can say then, well, what if we keep putting more carbon dioxide into the atmosphere? Then we expect that, that the climate will do, such and such. So that's the way we do it. I don't know whether I've got a slide here or not. I don't think I have. No, I don't have a slide in this package. I can find one if necessary, but...
Good morning. I'm Paul Matthews, environmental science. And we did talk a lot about the Great Ocean Conveyor Belt, and with ice caps melting in the Arctic and Antarctica. What are your thoughts on the thermohaline circulation, and is there a tipping point where if the Great Ocean Conveyor Belt stopped, it would cause a major disruption in the possible ice age for our planet? What are your thoughts on that particular topic?
Yeah, so I showed this picture here of the changes in the ocean heat content. The oceans are warming up, but there are other changes that occur within the ocean, and so these relate to the ocean currents. In the Atlantic, one of the key ocean currents is the Gulf Stream, and the Gulf Stream is the upper part of what is sometimes referred to as the meridional overturning circulation or the thermohaline circulation. It used to be called the thermohaline circulation. Thermo refers to temperature, haline refers to salt. And so if it's cold and it's salty, the ocean is more dense. And it's cold, salty water in the north tends to sink, and it creates an overturning circulation, and it's a key part of of what happens in the North Atlantic. And so when there is global warming, the odds are that there will be changes in the ocean currents. And one of the potential changes that occurs is that the warming, the Gulf Stream may not penetrate as far north, up towards the UK, to England, and to Iceland. And if that were to happen, then it could actually cool off in that region a little bit. Now, all of our experiments with climate models suggest that it just doesn't warm up as much in that region. It doesn't actually cool off. But this idea was taken by people who made a movie called The Day After Tomorrow, and they actually somehow turned global warming into a major ice age and cooled off the whole planet in the process because of the changes in the ocean currents. Now, that was science fiction. That's not really what's going to happen, but it does indicate that changes in the ocean currents can be very important, and these have consequences for fisheries as well, and they are certainly important for the regional climate. Does that answer your question?
Yeah, and I just have a follow-up question. We know that Miami, Bangladesh, low sea level places are at high risk, and we know that there's drought and we saw flooding. We know there are a lot of places that are going to have some trouble. Where are some places that are going to thrive from this? Are there places that are going to benefit from this, or be somewhat, I guess, safe or sustainable or livable?
So the projections into the future are that the biggest warming occurs in the Arctic, and then the second biggest warming occurs over land in continental regions, especially in the northern hemisphere. And there's a risk that in the subtropics things dry out more. There's more risk of drought especially in the southwest, and sea level goes up in all coastal regions. The places where the slowest increases occur are likely in the southern hemisphere because Antarctica is big and cold and white, and one of the best places to be is probably my home country, New Zealand, if you want to choose. But yeah, this is one of the problems in planning for the future. One should take these things into account. And as you mentioned, Miami already, because of that 3¼ inch rise in sea level since 1992, they have so-called sunny flooding. On sunny days, there's water at high tide in the streets.
Pumps. So they raise the road and build pumps to
yes.
flood it out. It seems like a Band-Aid.
So that's one of the sorts of things that can be done. And it relates to the time horizon. So you can bring the road up 8 inches, a foot, and buy some time. But it doesn't really solve the problem ultimately. And this is a big question around the coast here for New Jersey with Superstorm Sandy. Should you just put things back the way they were so that when the next storm comes along, it'll wipe it out again? Should you retreat from the coast a little bit? Should you put up barriers, walls, dikes of some sort, as they have in the Netherlands? These are serious questions, and some politicians are taking them seriously and really want to plan. But there's a large contingent that have their head in the sand. This is the ostrich with his head in the sand. He doesn't want to know. They don't want to know these facts. They don't want to have to deal with them.
Last question, then I'll go. What are your thoughts on the April 29th climate march? Are you going to be an advocate there? Are you participating? Or?
You said April 29th. This is April 22nd, I believe is Earth Day.
There's more than one.
Yeah, there's probably more than one.
There's one in D.C. on the 29th, there's one on the 22nd. Or maybe I have the date wrong, we can Google it, I guess.
Yeah.
But I just want to know your thoughts on that, if you feel like that's going to create any type of movement or...
Well, you know, scientists are actually very conservative from a political standpoint, or at least climate scientists are. And you know, when this was first announced, I wondered, you know, what happens if you have a march and nobody comes? You know, that would be a bit embarrassing. But, you know, there's a lot of other scientists or people who are not necessarily climate scientists who are certainly intending to march. And there are marches being organized around the country. Now, I won't be in Washington, D.C. at that time, but I am planning to march in Denver, I believe, if that happens. So there's an opportunity to show a little bit of activism here. And the reason for the activism is really because the Trump administration has not appointed a science advisor and seems to have climate, all aspects of climate, not just climate change, on the hit list of his targets. And so there are many things that are potentially being adversely affected by this, including our ability to track El Nino. This has huge consequences as a result.
Hi, I'm Jamie Kay, and I teach environmental studies. About weather variability, and I'm just kind of curious about the way climate models sort of the ways that they might be predicting more variability in the future. Is there an unpredictability that we need to be worried about?
Well, yes, and it relates to which variable you are looking at. And so as you go into the future, the biggest increase in the variations are associated with the water cycle. And so as I indicated, you end up with stronger droughts and stronger floods. Well, people say, well, how can you have both floods and droughts at the same place? Well, of course, it's not the same place at the same time, but it's at different times. And many of us have actually experienced this, but you can see it also at different places at the same time around the country. And so the greatest increase in variability is associated with longer dry spells and a greater risk of drought and water resources shortages. And then on the other extreme, when you do get the rains are stronger, they're heavier, there's a greater risk of flooding. Now I say risk of flooding because you can potentially manage the water. One of the challenges for water managers is to save the water from the times when you've got too much for the times when you don't have enough. And so this relates to whether you can build reservoirs or whether you can inject water back down into the ground to replenish the reservoirs below the ground, the natural reservoirs below the ground that are being depleted by pumping water. This is one of the sad things in California. California has been pumping water, groundwater, out of the ground, and in a lot of places, the ground has subsided. The ground has actually sunk as much as a foot in the Central Valley. And unfortunately, you can't put that water back. One of the big challenges, if any of you have brilliant ideas in the future, how to manage water better, how to pump water back into the ground, then these are some of the challenges that are before us. But how to manage water is a key issue. Now, we also do run into heat waves, really hot conditions. There are increasing numbers of heat waves around the world and in the US. And these may not last very long, but they can have huge consequences. They can have huge consequences on our crops, on animals who can't go inside and get into air conditioning and so on. Increased risk of wildfire is the other component of that.
Yeah, I was struck by the graphic you had showing the overall increase in precipitation across the U.S. despite the fact of that huge drought 7 years ago in California. I was even surprised to see that there was a positive increase over in the western part of the country as well. So.
No, the increase has been mainly east of the Rockies.
Oh, I saw that, but it seemed like overall there was an increase everywhere. Unless I misunderstood that.
So this is you can do this state by state. You can actually download this information. You can plot these things, and this increase that occurs around about here is mainly east of the Rockies, and in fact in the west there has not been an increase in precipitation. But there are increases in extremes. When it does rain, it rains harder. Those are fairly universal. So that was the other graphic I had related to. Where's it gone? I've lost it. Oh, this one here. Yeah. This one here, the increase is in the heavy rainfall events. Now, if there's not much change in the total amount, but the heavy rainfall events are increasing a lot, that also means that the dry spells are longer, and that these two things actually tend to go together. You tend to get these longer dry spells, and those are the sorts of things that stress plants. So dealing with precipitation, you want to be aware of the differences between the amount versus the intensity and the frequency or the duration of events. All of those are factors that are important.
Yeah, thank you. I read that incorrectly. Thank you.
My name is Charlie Apple. I teach human geography here. Within the last week, I've been asking my students to assess the water stress crisis and to try to understand the urgency of that crisis. Certainly you've spoken about the way that water around the world is changing. I asked them on a scale of 0 to 10, if 10 being keep and miss a crisis level of urgency, drop everything and deal with this right now. In 0, it's not a problem, we can take care of it later, just a kind of blasé attitude. Given all the changes that are occurring, if you can give a time frame and a level of urgency on a 0 to 10 scale in which the world and specifically the United States would need to be dealing with this. And, for example, I had one student suggest that maybe this is an 8 out of 10 because things like ISIS and things like other geopolitical concerns are of greater priority to us. If you could comment on how quickly we need to kind of have the willingness to address this.
We need to continue to address this immediately. The projections into the future are talked about in the Paris Agreement that was led by the U.S. President Obama in December of 2015. And what was talked about there was to avoid an increase in the global mean surface temperature of 2 degrees Celsius. That is symptomatic of all of the other things that are occurring in terms of the rainfall and the extremes and everything. 2 degrees Celsius. 2 degrees Celsius at our current rate, we will get to somewhere around about 2050 to 2060, somewhere in that time frame. And that's about the time frame when carbon dioxide will have doubled in the amount from pre-industrial levels. So I said to you before that carbon dioxide has gone up by 40%, and the temperature has already gone up by of order 2 degrees Fahrenheit, 1 degree, 1 plus degrees Celsius. Let's find that graphic. So that's this one here. Oops. There we go. So this is the pre-industrial temperature, and we're up around, you know, we're halfway, we're maybe a little over halfway there, 1 degree Celsius, and we're already seeing clear signs and adverse effects of climate change. When you get to about 2 degrees Celsius, many of the ecosystems are no longer viable where they currently are. That means that forests, trees will no longer grow back where the current trees are. It doesn't mean that trees won't grow there, but they'd be a different species. The trees that currently grow there have to move further north or somewhere else. The farming that occurs is no longer viable where it currently is. Whoops. And so this is about the time when there are really potentially catastrophic consequences occurring. Now, carbon dioxide has a long lifetime, hundreds of years, and that's why the carbon dioxide record keeps increasing. This is the black curve on here. We have to level that off and bend it back down, and it's going to take 20 or 30 years to do that, even if everybody pulls together around the world in order to do that. If this keeps going up, we're headed for this 2 degrees Celsius and potentially disastrous changes in all of our ecosystems and our ability to grow plants and so on, somewhere in the mid to, you know, a bit after the mid-century. So this is potentially in your lifetime. But it means we need to start now. If we were to start now with more fuel-efficient cars, we've got electric cars, we need to encourage more of those, but cutting down on the big coal-fired power stations and industry, and gradually transitioning those into other ways of doing things, using a lot more renewable energy, solar and wind and hydroelectric power and so on, then there could be some really major changes that will occur in your lifetimes. And they could occur given the right incentives. So some politicians talk about having a carbon tax. Maybe one that might relate more to you. How many of you drive? Are you old enough to drive yet? Yeah, I don't know whether you've experienced a Prius or a hybrid vehicle and how many miles it gets per gallon. But what would happen if there were a 1 penny a gallon tax put on? You wouldn't even notice, right? What happens if it was a penny every month? Think about that. That's about a quarter in 2 years. In 10 years, you're getting to be more substantial. So what happens when you're driving your car? You don't think much about paying an extra penny for gasoline, but paying an extra $2 for gasoline suddenly you think, next time I buy a car, I'd better buy a more fuel-efficient car, right? And the demand for the public then puts it on the car companies. And the car companies start to respond, and they build better cars. And they can do it. I went to a major convention of car companies. I was invited speaker there, talking about climate change to them. And these were the people that manufacture all of the ball bearings and the engines and the transmissions and stuff like that. They said, we can build better ones. We can build better, more frictionless ball bearings, but they cost more. And so if you had a car that got 5 miles per gallon better gas mileage, but it cost $500 more, it looked exactly the same, would you buy it? Well, if gas is $2 a gallon, maybe you wouldn't. But if gas is $6 a gallon, $6 a gallon is routine in Europe, maybe you would. And so the economics can change things. But it doesn't mean that it's actually going to cost more to drive, because the cars become more fuel efficient. And the same thing applies with big trucks and tractors and so on. At the moment, the incentives are not there. This is where the marketplace comes into play. The private sector comes into play. But the government has a role also in helping to set the stage for this. So that's the sort of thing. You can talk about this kind of thing. What would you do in order to encourage a gradual transition, not an abrupt transition? You don't want to do this abruptly. You can't say, switch, everyone, now drive an electric car. You can't do that. It takes, an average car has a lifetime of what, 12 years. So in 12 years, you can get different cars. In 24 years, 2 generations of cars, you can have a completely different fleet of cars. But if you're dealing with coal-fired power stations, a coal-fired power station has a planning lifetime of 35 to 40 years. And you can't just write those off. But after 35 to 40 years, you want the utilities to do something different. They should have a wind farm off the coast. They should have a solar farm. They should have a major wind farm up in Wyoming or something. There are ways of doing this and moving into the future. But these are some of the challenges that you guys are going to face. But you can also be a part of the solution. And if you've got really bright ideas, you can make a huge amount of money doing this as well.
Hello, my name is Jason Kearns. I'm a sophomore here at Wood. I just have a couple questions. Like, what were you saying about the cars and everything, like, pay like only $500 more for like a better car? Let's say we got like everyone in like America or like around the world to go electric cars, even though they're very expensive. What would happen then? Then it would cause a lot of people their jobs, such in the oil industry, because then there would be no more demand for those type of like supplies and fuel. So would it really be the best option? Because then it's causing so many people their jobs to make these electric cars.
I didn't quite catch everything you said, but the question is about everyone driving cars around the world and so on. I mean, it's one thing for, you can understand maybe the situation in the US, and there's already been a move towards more fuel-efficient cars and more electric cars and more hybrid cars in the US. But the real problems, the main reason the carbon dioxide keeps increasing here is not so much because of the US. The US is more responsible for this, if you add it all up over time, than any other country. But in recent times, in the last 5 years, the lead producer of carbon dioxide in the atmosphere has been China. And so there are, billions of people over in China. And many of them have lived with a very low standard of living over time, and the government has tried to increase the standard of living of everybody. One of the goals is to bring some electricity to everybody so that they can have a small refrigerator. Well, that seems a very desirable goal, right? And so they started building a huge number of big coal-fired power stations. Coal was cheap. But what happened was that they polluted their skies, and they started killing a lot of their people. And even I was involved in an international meeting in 2007. At that point, the Chinese government were very strongly opposed to any international agreements relating to climate change, because they had their economic goals and they wanted to produce electricity regardless. That has changed in the last 5 years in China. And the reason is because the Chinese scientists have pointed out, look, it's not just the fact that there's a tremendous pollution and very bad quality air that we have to breathe, but also it's increasing the droughts in parts of China. It's increasing the floods in other parts of China, along the Yellow River and so on. There are consequences for the climate change and the monsoons for China. And so they have changed altogether. And the Chinese government is now trying to reduce the amount of fossil fuels that they're generating. But one of the status symbols in China has been to own an automobile. It's a lot like it used to be back in the 1950s or 60s in the US. You got to have a big fancy car. That's a status symbol. It's very unfortunate to see this happening in China. In Beijing, they have 6 ring roads. 6 roads, ring roads around Beijing. You can get on the ring road, you can go around, but you can't get off. There's nowhere to go. But there's thousands of cars there now. It's a growth industry. But they can do it also with electric cars, and then they're non-polluting. And it's the same thing is beginning to happen in India. There are billions of people in India who are trying to upgrade their standard of living. And so these are some of the challenges. And one of the questions, one of the big issues in the Paris Agreement was how could India improve the standard of living of all of their people without using cheap coal energy? And the US government and people like Al Gore actually played a role in helping to bring India to the table and to produce and to release some technology to the Indians so that they could produce clean energy. And you can think about this happening also in places like Africa. You know, Africa also, there's a lot of people in substandard conditions, living on a few dollars a day with no access to electricity. But now you can see a thatch hut, and it's got solar panels on the roof. And for once, they can actually read at night or something like that. So the living standards are changing. And so what the US needs to do, in my view, is to play a leadership role to help that happen. And it benefits the US because we're all on the same planet. We're all on spaceship Earth. We have to share it. The atmosphere is a global commons, and the ocean is a global commons. It's shared by everybody, and now there's a lot of everybody's out there. I don't know whether that really answered the question, but...
Hello, my name is Sunny, and I play from the New Sciences Institute. My question is specifically about climate modeling. And Professor, I heard that the differences in predictions by the various climate models, such as that of, say, IPCC, AMS, or the Earth. I think the Earth assumption does want to arise from the fact that these climate models have thousands of parameters. And these differences come from the fact that these parameters are different because they have a degree of uncertainty. So do you know what these parameters are?
Yeah. There was a question earlier about, you know, the attribution issue, and I've just pulled up this here. Whoops. What did that say? So, as I said before, you know, with models, we can sort of play God. We can run these models with and without human influences. I'll put them both up here. And so at the top, you can see the black curve is the curve, the observed global mean surface temperature. And then underneath, you can see there's two sets here. One of them is called CMIP3. This is an older version of climate models. There's about 20 of those models. And then CMIP5, there's about 30 of these models. And they're all plotted, one on top of the other. So the weather in any one year, because of El Nino and natural variability, can be anywhere. And so you can see the range of variability here. And then there are these spikes down. The red curve is the average of these values. And these spikes down here are big volcanic eruptions that were put in. And so there were big volcanic eruptions. This is Mount Pinatubo in 1992, the last major volcanic eruption. It produces a cooling here. And there was a small cooling in the observational record as well. But this is what the estimate is, what would have happened. And you can see all of the models in here, and the CMIP5 models, the more recent ones, the yellow ones on here. You can see the range of what they're suggesting, what the spread is about these. And then you can see what happens if we now add the increases in carbon dioxide and other greenhouse gases. And we can sort of match reasonably well what has actually happened. And so the differences, there are a lot of things that you can play with in these models and different components. So there's the sea ice, the land ice, the glaciers, and you can look at those and see how well you can replicate the changes over time, all by themselves. You can look at the ocean as best we can, and so reconstructing what's happened in the ocean is an important part of that. And there are some things that, we don't know exactly, where you have to test and tune these, and there's different ways of doing that, and different groups make different decisions, which is one of the reasons some of these differences between models actually occur. But overall, there are enough constraints and at NCAR, we don't actually try to replicate the 20th century. It just comes out of the results of doing everything else that we do. Some of the trickiest parts relate to air pollution. And a part of that is because air pollution blocks the sun, but also air pollution affects clouds. And it changes clouds. It changes the number of drops in clouds. So that if you have certain kinds of air pollution, let's say you have a cloud and it's got a certain number of drops in it, and then you add some air pollution to it, typically you'll end up with a lot more smaller drops. And if you have smaller drops, so that there's the same amount of water in the cloud, same amount of potential rain, the cloud looks brighter when you look down on it from space. And so this is one of the things which is not quite done right, I think, in climate models yet. Climate models are a tool. We refer to them as models. They really should not be used as black boxes. You don't just plug things in and say, all right, here's the answer. Rather, you use them in an intelligent way for planning purposes, and that's the way we try to use those. And so, as I mentioned before, we can ask what-if questions, and we can say, well, what happens if we keep doing this into the future? I'll see if I've got one here. I don't have one here on this particular slide, but did I answer your question?
Yeah, thank you. Okay, we're going to dismiss in a minute or two. I just had one final question. Did you want to comment really briefly on what your most current work is dealing with, what you're spending a lot of your current time on? Just a minute.
I nowadays deal with the global energy and water cycle. And so the graphic I showed you of the ocean heat content, I was a contributor to that particular paper. And we have been spending quite a lot of time looking at what I call the characteristics of precipitation, trying to understand not just the amount, but also the frequency, the intensity, and the duration of precipitation, and how it's changing with climate change and how it's going to change as we go into the future. And it's not easy because although farmers go out and make measurements of rainfall every day, that's just one measurement. And what we need are hourly values because it doesn't rain all of the time, right? And so you have to have different kinds of measurement systems, recording systems. And a lot of these recording systems only go back 20 years or something like that. And so we don't have really good records as to exactly how the frequency and the intensity have changed over time. I showed you some numbers, and a lot of those are based upon daily intensities rather than hourly intensities. But that's one of the things that I'm working on, one of the challenges. So dealing with the complexity of precipitation is one of the tasks.
Before we leave here, just please, one final thank you for Dr. Trenberth.